Every system design interview, at some point, will ask you about databases. And one of the first decisions you'll need to defend is SQL or NoSQL. This isn't a religious debate, it's an engineering decision with clear trade-offs. And knowing those trade-offs, not just the definitions, is what separates a good system design answer from a great one. Today, we'll cover what relational and NoSQL databases are, the real differences between them, the different categories of NoSQL databases, and the decision framework you'll use in interviews. Relational databases have been the backbone of data storage for over 40 years. PostgreSQL, MySQL, SQLite, these are relational databases. Data is stored in tables with rows and columns. Relationships between entities are expressed through foreign keys and join operations. The schema is defined up front. You declare what columns exist and what type of data each one holds before you insert a single row. The most important property of relational databases is ACID compliance. ACID is why banks use relational databases. If you transfer money from account A to account B, that operation is atomic. Either both the debit and the credit happen, or neither does. You will never lose money in the middle of a transaction. Relational databases are also excellent for complex queries. SQL is extraordinarily expressive. You can join data across multiple tables, aggregate, filter, and sort in ways that would be extremely difficult with other storage systems. Let's be concrete about what ACID in practice looks like. Suppose you're building an e-commerce checkout. Decrement inventory, create an order record, charge the customer, and send a confirmation. That's 4 separate database operations. With ACID, all 4 succeed, or all 4 fail. The customer is never charged without an order being created, and inventory is never decremented without a corresponding order. This is why, 40 years after COD and Date formalized the relational model, PostgreSQL and MySQL still run the financial core of most companies on Earth. Correctness compounds. When the cost of a wrong answer is high, you pay the price for ACID. Relational databases are powerful, but they have scaling challenges. They scale vertically very well. Throw more hardware at them, and they get faster. But horizontal scaling is hard. Spreading a relational database across multiple machines requires careful thought about which rows live where, how joins work across machine boundaries, and how to maintain consistency. The schema-first approach is also a constraint. In a fast-moving startup, your data model changes constantly. Every schema migration requires coordination between engineers, careful planning, and often downtime. For certain workloads, this rigidity is a serious bottleneck. These limitations are what motivated the rise of NoSQL. Consider Twitter at scale. At peak, Twitter processes roughly 6,000 tweets per second. Each tweet must be fanned out to the timelines of every follower. A user with 10 million followers generates 10 million write operations from a single post. No single relational database can absorb that write volume. The schema-first model also struggles. A tweet might have location data, media attachments, poll options, or thread relationships. And these attributes vary per tweet. A rigid relational schema fights against this kind of heterogeneity. This is not a failure of relational databases. It's a signal that relational databases were optimized for a different set of constraints. The constraints of the 1970s mainframe world, not the constraints of a planet-scale social network. Different tools for different problems. NoSQL doesn't mean no SQL syntax. It means not only SQL. These databases prioritize flexibility and horizontal scale over the strict guarantees of relational systems. There are four main categories of NoSQL databases, each designed for a different type of data and access pattern. Let's make the document store concrete. Suppose you're storing product catalogs for an e-commerce platform. Product A is a t-shirt with attributes: size, color, material. Product B is a laptop with attributes: CPU, RAM, storage, screen size, weight. In a relational database, you'd either have a table with columns for every possible attribute, mostly null, or you'd normalize into a key value attribute table, expensive to query. In MongoDB, each product is a document. The t-shirt document has size, color, material. The laptop document has CPU, RAM, storage. No nulls, no awkward joins. Each document describes exactly what it is. Now, let's make the column family store concrete. Cassandra stores data in wide rows. A row might have a user or ID as the partition key, and then hundreds of timestamp sorted columns representing activity events. Querying the last 100 events for a user is a single partition read, extremely fast. This is why Cassandra dominates IoT telemetry, activity feeds, and time series analytics, and graph databases, the overlooked category. If you need to find all users who are second-degree connections of a given user in a social network, a SQL query would require multiple self-joins on the user's table. In Neo4j, that's a two-hop graph traversal. At millions of nodes, SQL takes minutes. Neo4j takes milliseconds. This is not an optimization detail. It's a fundamental algorithmic difference. Base is the philosophical opposite of ACID. Where ACID prioritizes correctness above all else, Base prioritizes availability. A base system will return an answer, even a potentially stale one, rather than refuse to respond. The name is deliberately a contrast to ACID. ACID is hard and precise. Base is soft and approximate. In chemistry, they're opposites. In databases, they describe two different bets about what matters most. Most internet-scale systems are base systems. Your Amazon cart persists even when parts of Amazon's infrastructure are unreachable. Your Netflix recommendation list loads even if the recommendation service is slightly stale. These systems chose availability over perfect consistency, and for their use cases, that's the right trade. The critical question isn't ACID or base, it's what is the cost of inconsistency in your specific system. For a bank transfer, inconsistency is catastrophic. For a social media like count, inconsistency is invisible to the user. Forget the rule, use SQL for structured data, no SQL for unstructured. That's too simple. Here's how to actually think about this decision. Use SQL when you need ACID transactions, financial data, inventory, anything where partial updates are catastrophic. When your data is naturally relational and you need complex queries across multiple entities. When your team knows SQL and the overhead of learning a new query model isn't worth it. Consider NoSQL when you need to scale writes horizontally at massive scale. Think Cassandra handling billions of writes per day. When your schema changes frequently and you need flexibility. When your access patterns are simple and well-defined, you know exactly what queries you'll run. When you're storing a specific type of data that a specialist database handles exceptionally well, graphs, time series, documents. In a system design interview, when asked about database choice, a weak candidate says, "I'd use PostgreSQL," or "I'd use MongoDB." A strong candidate asks 3 questions before naming anything. Question 1. What are the consistency requirements? Does every read need to reflect the most recent write, or is eventual consistency acceptable? If you're building a payment ledger, you need strong consistency. If you're building a social feed, Eventual consistency is fine. Question 2. What are the access patterns? What queries will be executed and at what frequency? If every query is a lookup by primary key, a key value store may be faster and cheaper than PostgreSQL. If you need to run ad hoc analytical queries across billions of rows, a column-oriented database like BigQuery or Redshift is the right answer. The access pattern dictates the data model. Question 3. What is the scale? How many reads per second? How many writes per second? How many terabytes of data? A single PostgreSQL instance handles roughly 10,000 transactions per second on commodity hardware. Cassandra on a small cluster handles millions of writes per second. DynamoDB delivers single-digit millisecond latency at any scale. And you pay Amazon to manage the infrastructure. Scale requirements filter your choices before any other consideration. After asking these 3 questions, state your choice and defend the trade-offs explicitly. I would use Cassandra for the activity feed because we need to handle 500,000 writes per second. Our access pattern is always fetch last n events for user X, and eventual consistency is acceptable for a feed. I would use PostgreSQL for the user accounts and payment records because we need ACID guarantees for financial operations, and our write volume there is modest, maybe 5,000 transactions per second at peak. That answer demonstrates systems thinking. It shows you understand trade-offs, not just technology names. Benchmarks give interviewers confidence that you've operated at scale, not just read about it. Here are the numbers that matter for database selection. PostgreSQL on a single well-tuned node. Approximately 10,000 to 50,000 transactions per second, depending on workload and hardware. Read-heavy workloads with a read replica pool can reach hundreds of thousands of reads per second. Write throughput is the bottleneck. A single PostgreSQL primary typically saturates between 5,000 and 20,000 writes per second. MySQL with InnoDB. Similar characteristics to PostgreSQL. Facebook ran its social graph on thousands of MySQL shards for years, not because MySQL is exceptional at scale, but because a known technology with enough shards can handle almost any load. Cassandra, on a modest 10-node cluster, handles millions of writes per second with linear scalability. Add 10 more nodes, add proportionally more throughput. This is the defining characteristic. Cassandra's write throughput scales horizontally with almost no architectural ceiling. DynamoDB, single-digit millisecond latency at any scale. Not fast, any scale. The P99 latency for a DynamoDB get item is under 10 nanometers, whether you have 1,000 rows or 10 trillion. This is the promise of a fully managed, pre-sharded, pre-replicated key value and document store. The cost is that DynamoDB's query model is intentionally limited. You must know your access patterns at design time. Redis, sub-millisecond latency for in-memory operations. Typical read latency is 0.1 to 0.5 milliseconds. A single Redis node handles hundreds of thousands of operations per second. Redis is the fastest general-purpose database you can deploy because all data lives in RAM. These numbers form the vocabulary of scale. When you say, "We expect 200,000 writes per second," you immediately know that PostgreSQL alone won't cut it, that Cassandra is purpose-built for this, and that DynamoDB with provisioned capacity is a viable, managed alternative. One important nuance: the SQL versus NoSQL decision is often SQL and NoSQL. Most mature systems use multiple databases for different purposes. Instagram uses PostgreSQL for user data, Cassandra for the feed, Redis for caching, and Memcached for session data. That's 4 databases serving different parts of the same system. In your system design interview, this is the right answer to give when asked about database choice. Identify the different data access patterns in the system and propose the most appropriate database for each. Uber is a canonical example of polyglot persistence done well. MySQL for their core business objects, trips, drivers, riders, where ACID guarantees are essential. Schemaless, their own document store built on MySQL for flexible object storage. Redis for geospatial indexing of driver locations, because Redis geocommands let you find all drivers within 2 km in microseconds. Kafka as a durable event log. Each piece of the system uses the right tool for its specific data characteristics. The lesson is not use more databases. The lesson is understand your data, understand your access patterns, and let those requirements drive your technology choices, not the other way around. There are 3 mistakes that consistently cost candidates points in database questions. Mistake 1. Choosing a database before understanding requirements. Saying, "I'd use MongoDB" before you understand consistency needs, query patterns, or scale is a red flag. Interviewers know that MongoDB is not always the right answer, and a candidate who jumps to it without analysis signals a superficial understanding. Mistake 2. Ignoring the operational cost of NoSQL. NoSQL databases are not universally simpler to operate. Cassandra requires careful capacity planning, compaction management, and expertise in data modeling around access patterns. DynamoDB is simpler to operate but more expensive and less flexible. PostgreSQL with a good DBA and proper indexing handles enormous scale and is understood by almost every engineering team. Factor in operational complexity. Mistake 3. Conflating NoSQL with unstructured data. NoSQL databases absolutely have structure. It's just that the structure is defined differently. Cassandra tables have schemas. MongoDB documents have an implicit schema enforced at the application layer. The difference is that the schema is more flexible and does not require upfront alter table migrations. No schema is not the same as no structure. SQL databases give you ACID, complex queries, and strong consistency. They scale vertically well, but horizontally with effort. Use them when data integrity is non-negotiable. NoSQL databases give you flexible schemas, horizontal scale, and specialized performance for specific access patterns. Use them for high-scale, well-defined workloads. The real answer is often both. Different databases for different parts of your system. When asked, "What database would you use?" in an interview, ask 3 questions first. What are the consistency requirements? What are the access patterns? What is the scale? Then name your choice and defend the trade-offs. PostgreSQL handles roughly 10,000 to 50,000 TPS on a single node. Cassandra handles millions of writes per second across a cluster. DynamoDB delivers single-digit millisecond latency at any scale. These numbers belong in your answers. In the next video, we go deeper into database scaling, sharding, and replication. These are the techniques that let databases handle the load that no single machine can. See you in video 6.